Okay, so this is the collection, but for many reasons we would also want to look at the unit disk. Okay, and remember what we have is h goes to d. Okay, this is h and this is d, and we have a fractional linear transformation, something of this form: z minus I by z plus I. Z goes to this. This is the map which takes it. Okay, I give this guy a name. Let's call this better to have a notation here, psi or something. C preserves circles, and here by circles I always mean circles and lines, and is an angles. So what does this mean? Hence geodesics. Oh, I should state one more fact for completeness. Okay, C takes R, or more accurately R union one point at infinity to boundary of this disk. Okay, so the boundary of the disk, and that's the reason why I wanted to turn to the unit disk, because this guy is going to be boundary of H in some sense, but we have one special point while boundary of D is a nice and symmetric circle. So C takes this to this. So what do we conclude from these two facts? So thus, okay, geodesics in D are arcs of circles intersecting boundary D orthogonally. Let me draw a couple of pictures of these. So I have the circle here, and here are a couple of arcs, right? So one of them could be like this, and it intersects here in right angles. But there's another possibility, which is simply diameters. These are lines rather than circles, but lines are circles as far as we are concerned. They're lines passing through the center. Other chords are not geodesics. Now you may be wondering about one question, which is how do we know these are all of them? I just took some and then took their images and got others. Well, given any pair of points, there can be at most one geodesic through them, and it's easy to see in both, maybe even easier in the hyperbolic disk model, that there is one in our collection which passes through any pair of points. Okay, so that tells you that these are all of them, because we have got plenty and we can't have more, because of otherwise we would have two geodesics through a given line, and both of them are strict minima, remember. Okay, so finally let me just go back to the historical roots of hyperbolic geometry. Okay, so parallel postulate, well, this is violated. This is a picture to keep in mind though. So let's take a big unit disk here, and let's take a straight line. This is a straight line, and let's take a point that's not on the straight line. Well, what does a parallel postulate say? There's a unique line which is parallel in the sense of not intersecting it, which passes through this point. Well, here's a line. Okay, line in the sense of a geodesic. It passes through this point and it is not parallel to it. Here's another. And there are plenty of them. Okay, so hyperbolic means actually moving away, and the point here is that given a point line and a point on it, there are infinitely many lines passing through that point which don't intersect the given line, which is what is classically called parallel. So this tells us what the straight lines are, how we work with them, and it shows in all other axioms are satisfied, of all the other Euclid's axioms are satisfied. So historically the importance of hyperbolic geometry was that it showed parallel postulate is logically independent of the others, because others are satisfied and the parallel postulate is violated.